Hello everyone and welcome back to Physical Geology 1403. Today is our exam 2 review, which means it is super casual, pretty informal, just getting you ready, answering your questions. Let's see, I left instructions at the end of the last lecture that if any of my students needed, or any of my high school students had questions, they should get them to me before this morning. I'm going through my email right now, and I'm not actually seeing any emails from them. But I'm going to go into the... no, that's the online class. I'm going to go in here and check. I have no messages on Blackboard either. So, I guess they have no questions. Just a real quick recap of something that you all just heard, but I'll repeat for them. So Thanksgiving holiday after today. Next week we'll have the last 2 lectures of the course. The week after that we will have our final exam review. And then the final exam. You will be getting the lab exam next week on Monday. Of course you have up until the last day to turn in retries of assignments, notes, and everything. Try and get it all done before then though, because I really want you to only be focused on the final exam for that last portion of the class, okay? I would love it if you had enough time to become comfortable with your position, with like where you are on all the other assignments before then. But of course, what you do with your time is up to you. It's not something that I'm going to dictate to you. All right, exam 2 is all about module 2, so lectures 8, 9, 10, and 11, right? Glaciers, deserts, running water, shorelines of the ocean floor, groundwater, all of those. Yeah, how we feeling about those? A good thing to do, by the way, for these review sessions, I'll just remind you, is to go through your notes for this module, see where they maybe were not as deep. Maybe you have half a page of notes for lecture 8 and 4 pages of notes for lecture 9. Might give you a good indicator for where you might want to focus your questions, right? If you're reading through it and there's something that you made note of, but you really just do not remember what it's talking about, this is a perfect time to ask. Flesh out those notes a little bit more. Yeah, your notes are your biggest guide for how these exam review sessions go. So I'm going to turn the time over to you now. Oh, a few more statistics actually. So your exam is going to be open throughout the whole break. All right? You probably want to take it before the break officially begins, so you have a nice relaxing break. But I will leave it open as an option if you'd rather take it after Thanksgiving dinner. I don't recommend that. You'll be pretty sleepy, right? But you'll have the option. Okay, so I'll have it set to close. I will change it so that it's set to close on, let's say, Sunday. Okay, so that gives you like 6 days to take it. And it's only 20 questions long, and you have the full 500-minute time limit to take it. And if 25 minutes a question isn't enough time for you, then there's a deeper problem we need to address, okay? Okay, so now that you have all the statistical data for that, Spill, what do you got? What questions do you have for me? And this review will go as long as the questions do. So if we go for some period of time without, having any questions and you guys feel comfortable, then of course I'm just going to end the review and open the exam and we'll be going from there. While you are looking, I'm going to show you this, get our day started. Sure you'll find it as amusing as I did. Sorry it's not big, but my friends just trying to live their lives, me about to tell them about another new dinosaur. Yeah, just thought I'd share that. So real, so true.
Do you think we could have like a quick review on Lecture 9?
Lecture 9, of course. Turn this off, if it'll turn off. 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 There we go. To wield it like a weapon. All right, sweetie. Okay, Lecture 9. Yes, what specifically about Lecture 9?
I feel like I wasn't here that day, and also you weren't here that day.
Yes.
And we watched the video, so I think it'd be a little bit best if we kind of get like a quick overview of it, if that's possible.
Sure, just about lectures, glaciers in general?
Yeah.
Absolutely. Okay, do you two also feel a little weak on the glaciers part? All right, yeah, that's understandable. I wasn't here. Let me go ahead and pull that PowerPoint up, and then we can do a Cliff Notes version. Nope, that's 1404. We're in 1403. Glaciers. All right, now let's put that back on. Easy, girl. All right. All right, what are glaciers? Well, okay, so I kind of start off by talking about water, some of the amazing properties of water, like why it's so cool. Pardon the pun. And mostly it has to do with energy and the states that we can find it in. Sweetheart, I'm gonna have to put you down for now, okay? Okay, so the states that we find it in. Actually, you know what? I could probably hold you at this angle now. Let's do that. That's a much better angle. Okay. Okay, so water as a liquid behaves in certain ways, and then as a solid behaves in mostly different ways. But some patterns that we see throughout this lecture are that they actually, regardless of state, water can behave in very similar ways to itself, right? And this is because of the physics and chemistry that makes it so different from other compounds. Okay. Water has cohesion, which means it likes to stick with other water. That's why when you put water down in drops, it stays in those sort of bubbles. Whereas with other liquids like oils, it'll spread out as thin as it can, okay? Less cohesive. It's very effective at absorbing heat, okay? And that's why it takes a lot of energy to heat up a water, but it also takes a long time for that water to cool off, right? It's very effective at holding that heat. You got to give a lot of heat for it to heat up, but that's because it's essentially acting as a battery for it, and then it slowly releases it as time goes on, more effectively than a lot of other materials. And then you've got icebergs, or excuse me, not icebergs. The concept that ice floats on water, which they're the same thing. They're the same chemical, the difference being the state of matter. And so why would one thing float on top of another thing? A change in density, which is what happens, okay? Most things, when you take them from a liquid to a solid state, they become denser. Because when things are in a liquid state, the atoms are not as attached to each other, right? And so there's more space between them. Versus water, on the other hand, which when it goes into a solid state, it actually expands outward. Its crystalline framework takes up more space than its liquid version of itself. And so it actually expands by about 9% or so, okay? That varies depending on the temperature it froze at and the temperature it's subjected to afterward. It could condense a little bit more, it could expand a little bit more, but about 9%, which is enough for the ice to float on water even though they are the same substance, okay? This concept of space between atoms, by the way, is fascinating. This has the potential to take me on another tangent. Do you want a tangent now or do you want a tangent later?
No.
Yeah.
Tangent now? Okay, cool. All right, so let's get quantum for a minute here, all right? When I say quantum, I'm talking about like subparticles, okay? The amount of space between particles, between atoms, and within an atom, way bigger than you would think, okay? If you took a football stadium and said, this is the size of my atom, including the nucleus and all of the electron orbitals, and then you put one piece of popcorn in the middle of that stadium. That piece of popcorn would represent the size of the nucleus, and that stadium would represent how large the rest of the atom is, how far away the electrons are circulating from that nucleus, okay? That's a lot of empty space. 99.99999999999% of the universe is empty space, including all the mass, because the amount of mass in just you and me is crazy, okay? But the amount of space within that mass, even crazier, right? They actually did an experiment on this. What was this guy's name? Gamow, I think was his name, a physicist named Gamow, I think, who did this experiment where he stretched a layer of gold extremely thin. Gold is the most malleable of all of the atoms, all of the elements that we have access to, okay? He made it extremely thin, like molecule thick, super thick, like only a few atoms thick, okay? And then he bombarded it with radiation. And some of it was reflected, but most of it made it through. Even though it's so thin, still a solid barrier. How did that happen? This can only happen if most of the space, most of the mass, most of the area, surface area of that gold sheet was empty. If it was empty space through which those atoms could pass, and it did. Only 1 or 2 atoms out of 1,000 were ever deflected or reflected. The rest made it through the gold. And it's really funny, actually, this story, because the way the story goes is the next morning, like he had nightmares all night. And the next morning, he was afraid to get out of bed because he was afraid that he would fall through the floor of his house. Because now he actually understood the reality of mass, that most of mass is empty space. An amazing discovery, right? And most people don't even consider this. Like, you are mostly empty space. And so is everything around you that you will ever see in our universe. Isn't that interesting? All right, tangent over. All right, moving on. Ice as a mineral, it's a solid component. It is, in fact, a mineral. Why? Because it matches all of the qualifications for what a mineral is. Solid, naturally occurring, inorganic, crystalline structure, right? And chemical formula. It has all of those things. Therefore, according to our definition, it is in fact a mineral, which is why geologists study it, okay? The studies of ice and glaciers falls under the realm of geology, okay? It behaves in a plastic manner. And without diving too deep into the thought process of this here, plastic is a word that we often think of as a subject, like, oh, this thing is plastic. Look, this remote is plastic. This table is plastic. But I want you to be thinking of plastic not as a subject, but as an adjective, okay? When we call something plastic, what does that mean? It is something that we formed into the shape we wanted it to be. Well, now that kind of is a little wishy-washy, because couldn't we call metals plastic? They behave in a certain plastic manner. Remember, we're using that as an adjective. Metals are not plastic, the subject, but we can describe them to an extent as plastic, the adjective. They are able to be shaped into something that we want them to be for a certain purpose. Plastic, the material, is really dozens and dozens of different chemical formulas that we use for different things. The plastic in your phone is not the same quality as the plastic in your car, right? I have a 3D printer at my house. I use PLA, I use ABS, I use TFF, I use carbon fiber, I use all sorts of different materials that we generally refer to as plastic. They're all plastic, but they all have different chemical equations, and they're all good for some certain things. Some are more rubbery, some are more rigid, some are hold up better at a temperature, some you can sand down easier. Whatever the purpose is, use the right plastic for it, right? So I want you to be thinking of it that way. Glaciers are plastic. What does that mean? That means that they deform according to a certain environmental parameter. In the case of a glacier, whatever the landform they're scraping over is. Okay, so they deform plastically, they reform themselves as they move downhill. Glaciers are just essentially really thick ice. Okay, that's really all it comes down to, is it's a lot of ice. And once that ice is thick enough, it'll start moving downhill under the influence of what?
Gravity.
Gravity. Gravity being a big force here. Okay. It can take a very long time for these glaciers to build up, thousands to even tens of thousands of years, right? There were glaciers more than a mile thick on top of North America during our last true ice age. We're technically still in that ice age, by the way. The definition of an ice age is when you have ice at both poles of the planet, and guess what? We still do. So technically we are still in an ice age, though we are on the way out as our poles continue to melt. Okay. What we refer to as the ice age, most people are usually referring to as what they're actually talking about is the last glacial maximum, which was the last time the glaciers were as far towards the equator as they were in the past. Okay, so the last time all our glaciers melted, and what we're looking at in the future, by the way, is going to look something like this. Okay, where if all of the ice, if the mass of ice on top of the continent of Antarctica, if it melted, you would look, or North America would look something like this, okay? Where pretty much all the east and south coast is underwater. Seattle's underwater because the Puget Sound is huge. San Francisco is underwater because the bay is huge, okay? All that ice melting would raise sea level 60 to 70 meters. And that's what we're looking at in a couple thousand years, okay? We are still a couple thousand years away from something this bad, but we are looking at perhaps a 10 to 12 foot increase by the year 2100, which is also not going to be great. You guys ever been to Corpus Christi? You like hanging out down there? It's all going to be underwater within 70 years. Okay? All it takes is 10 feet more of water, which we will reach by then, and that entire region is underwater because it's only a few feet above sea level right now. Okay? So that's what we're going to be looking at. Your great-grandkids won't be able to go to vacation at Corpus Christi because the city will be underwater. Okay? All right. Valley glaciers. So I'm just kind of going to breeze through the different types of glaciers here. Valley glaciers are your kind of typical, when I say glacier, this is what you're thinking of. Massive ice flowing down a valley, a U-shaped valley. I'll describe how those form here in a minute. This is an example of a couple of them. They are bringing sediment down here with them. Those are called moraines. We will talk about those when we discuss glacial features. So those are valley glaciers. Then you have ice sheets. There are only two ice sheets on our planet right now. Okay, the one on Greenland and the one on Antarctica. I do need to say on future labs, discussion boards, perhaps if there's a question on an exam about this, remember that Antarctica has a T in the middle and a T at the end. I've seen it Antarctic and Antarctic. Just remember there's a couple of T's in there. All right. An ice sheet is when you have a central source of ice. So you get a lot of snowfall in a central area, in the case of Antarctica, right here around the South Pole, and it kind of spreads out from there. The glaciers in this whole sheet kind of source out from the middle here and spread out from that central location. In the case of Greenland, it's getting a lot of ice up here near the North Pole, and it's spreading out across the island that way. Okay. Then we have ice caps, which are essentially smaller versions of ice sheets. They do not take place over an entire continental area. Usually they just cover a sort of mountain range, but the same sort of concept. Multiple glaciers flowing from a central source. Okay. And then you have outlet glaciers, which are essentially glaciers that have escaped. They've made their way out from the rest of the pack from an ice sheet or an ice cap. And then you have Piedmont glaciers, which make this very interesting, unique shape when they spread out after they have escaped from a valley. Does that shape look familiar? What else does that?
Rivers?
Rivers? Rivers. We call that, if we would see that in liquid water, we call that a delta or an alluvial fan. Remember that? Ice is doing the same thing. This is what I was talking about earlier. Solid water and liquid water will behave in the same way a lot of the time because the physics is the same, just affecting it over different periods. Remember I told you about, and when we were talking about deserts, we talked about sand seas with those longitudinal dunes. Yeah? This is essentially the same thing, okay? Where the physics is the same, it's just affecting a material over longer periods of time, ending up with a very similar effect. All right, so let's talk about glaciers. To make a glacier, you need snow. Where do we get snow? Either you have to have very cold temperatures, closer to land, or where can you get very consistently cold temperatures?
Near the poles.
Near the poles, absolutely, which is why there's ice caps. What else?
Higher elevation.
Higher elevation, there you go. The higher up you go in the atmosphere, the colder it gets because the atmosphere isn't as thick and therefore there isn't as much heat held into in the system up there, okay? So, higher elevation. There comes a point when you go high enough in elevation when you reach a line called the snow line. The snow line is the point up there, the line up there, above which snow can remain year-round. So whenever I have mountains that are above the snow line, I'm going to start developing glaciers up there because the snow falls, doesn't melt, remains, gets thicker, 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 and turns into that ice, okay? So that snow is deposited as hexagonal crystals, which we're all familiar with, right? I mentioned this in the lecture, but we all learned as a kid that no two snowflakes are alike. Right? Maybe your kindergarten teacher made you feel super special by saying that you were a little snowflake and you're not like anyone else. As true as that may be, snowflakes are in fact restricted to a certain number of forms they can take. There's, I want to say, 26 different hexagonal crystalline forms that have been recorded from snowfall. Okay? So there is a finite number that they can take. That myth probably started because the likelihood of finding any two that are the same shape out of the total number of 26 possible ones, right? Unlikely. And so when people would be like, oh, okay, that's the shape. Oh, that's that shape. Oh, that's that shape. Oh, that's that shape. That's probably where that myth started. No snowflakes are alike. Actually not true. Okay, so here's a picture of Mount Kilimanjaro, which is in Tanzania, okay? Africa, as you can tell. Giraffe, right? There's snow up there. You wouldn't typically think of snow and Africa in the same sentence, and yet here we are. What's happening here? That volcano must be what?
Above the snow line.
Above the snow line. Where do we see the snow? Right there. That must be where the snow line is in the atmosphere in that part of the world. And therefore, snow remains, and you can see that there's even glaciers up there near the top, making their way down the valleys. Okay, so how do these glaciers move? This plastic flow happens after you get a certain amount of mass. Once your ice has reached a certain amount of mass, then it is going to be heavy enough under the influence of gravity, because remember, heaviness, weight, is a product of both the presence of mass and gravity. Okay, both those things together make weight. If I were in space, I would still have the same mass, just be weightless. But here on Earth, we have a certain gravity constant because of the mass of our planet, giving us weight. Okay, so once we have enough mass buildup, then the weight has accumulated to the point where it makes enough pressure on the ice at the bottom of my glacier that the ice on the bottom of my glacier starts to deform plastically. That is essentially shape itself, contour itself according to whatever the surface it's on. And that way it starts slowly moving downhill. Imagine if I had a brick. Let's go with something heavier, actually. Imagine if I had a 4-ton brick, okay, on a slope. Under normal circumstances, that brick might not move, but what if I turned the bottom foot of that brick into Play-Doh? All of a sudden, the weight of everything above that Play-Doh is going to start squishing and squeezing that layer of Play-Doh down, and the top of my brick is going to move downhill over the deforming Play-Doh part of itself. Okay? That's what's happening here. Okay? It's deforming plastically, like Play-Doh would. Now, how healthy, how large, how long-lived a glacier is largely dependent on a budget. Not a budget of money, a budget of snow. More snow input means glacier gets more mass as time goes on. Less snow input means glacier gets less mass as time goes on. However, there's always a constant here. That constant is it's always melting on the bottom part, right? Wherever the bottom of my glacier is, it's always going to be melting there. So the ratio of snow input versus ice loss is going to be my budget, okay? And this will determine whether my glacier is advancing or retreating. Anything below the snow line, we call it the zone of wastage because it has the potential for melting and falling off. Anything above the snow line, we call it the zone of accumulation. If the gain in the zone of accumulation is bigger than the loss in the zone of wastage, the front of my glacier will always keep moving downhill. If the loss in the zone of wastage is greater than the amount of gain in the zone of accumulation, the front of my glacier is going to melt faster than the back can keep up with it, and the front of my glacier is going to melt uphill. Now, this is not to say that a retreating glacier is one where the front is being pulled uphill. Glaciers can't fight gravity, nor do they have a brain. They cannot physically pull themselves uphill. The front is simply melting faster than the back can keep up with, right? Imagine it. This is a really weird example I gave last semester, but it was funny. Imagine if I had a 10-foot Subway sandwich, right? Like this 10-foot Subway sandwich, and Joel was really hungry, and I was pushing the Subway sandwich towards his face, okay, at like a foot a minute, but he could only eat a couple of inches every minute because he's not insane, right? His face would have to keep getting like, right? I would keep shoving the sandwich towards his face. That's an advancing sandwich, right? But if you were really hungry and you were a champion at eating contests or something, and you were somehow able to eat that sandwich at a faster rate than my sandwich than the rate I'm pushing it, the front of my sandwich would get eventually pushed closer and closer to me, even though I'm continually pushing it towards you, right? Same concept here. Advancing versus retreating sandwich. Silly, like I said, but you get the idea. All right. So let's talk about some of the things that glaciers do. Glaciers are extremely powerful forces of weathering and erosion, okay? They weather pretty much just through physical, mechanical weathering. How is that? We're talking about millions of tons of ice. And even though ice is not as hard as rock, there's a lot of it. If I dropped a ton of feathers on you, would you die? No?
Yeah.
Yeah, you would. Which one's heavier, a ton of feathers or a ton of bricks?
Depends on the day.
What was that?
Depends on the day.
Depends on the day? It doesn't, though. Depends on the planet, but it doesn't depend on the day. They weigh the same because a ton is a ton. Sure, I might have to pack those feathers in real tight to reach a ton, but it would still be a ton. A ton of feathers would still kill you. It would smash you flat just like a ton of bricks would. That's the point of a ton, right? So even though ice is not as hard as the rock it's scraping over, there's a million tons of it pressing down on that. And it's going to pulverize that rock. It's going to scrape it. It's going to absolutely destroy that rock surface that it's scraping over, okay? Mechanical weathering. Glaciers, very powerful forces of mechanical weathering, okay? But then there's also the erosion component. It's picking up that material and carrying it downhill. At what point does it drop it? When is my glacier going to drop the rock material it's carrying? Whenever it melts. Wherever the front of that glacier is currently melting is where that material gets dumped. Okay? So it is both weathering and eroding at the same time here. Okay? We call, when it picks up a large chunk of rock, we call that plucking. And whenever it scrapes material off of a surface, we call it abrasion. Okay? When a chunk of ice falls off the front of my glacier, we call that calving. And that's usually where you get icebergs that fall into the ocean. All right, some of these glacial landforms that are formed through the process of these weathering and erosion. You have your valleys, which usually start off as small little stream or river valleys, and then my stream or river ends up freezing and then becoming a glacier, and then that glacier moves downhill, and it scrapes out that valley wider and wider and wider as time goes on, all the way down to where? Where is water always trying to reach?
Sea level?
Sea level. Bingo. Glaciers are no different. They're trying to reach sea level as well. Okay? A cirque is kind of one of these side valleys here that is kind of a tributary that feeds into the main glacier. An arête, these are your long, oh, careful, sweetie. These are your long ridges, very sharp ridges here between my cirques and my valleys. And a horn is where multiple arêtes come and meet together and make a very sharp-looking peak. Okay? A fjord. A fjord is what happens when climate shifts towards the warmer. What happens to my ice as climate shifts towards a warmer environment?
It goes eroding the landscape around it, and is it that why fjords are like kind of like a valley?
That's already happening, whether it's warm or not.
Oh,
What's happening to my ice as the conditions warm up?
melting
Melting. Where's that water going to go?
down towards sea level.
Down to sea level. And what happens when it reaches the sea?
It becomes like a stream or like a river. No.
Huh?
Or that it becomes like a. It starts forming into like a stream or like a river since it's like no.
I mean, yeah, there's a river flowing down there, but I'm asking what happens to sea level as all that water reaches it.
It goes up.
It rises. So what's going to happen here is during the last ice age, when all of these glacial valleys were being carved out on their way to sea level, and then I reach a period of global warming, that sea level is going to rise as my ice melts. What's going to happen to my valleys? They're going to get filled in by water. They're going to get drowned. They're going to get flooded. A fjord is a glacial valley that has become flooded by rising sea level. That's what a fjord is. Another feature you might see is a roche montagne. It's French, but I do not speak French, so I apologize to any French speakers out there. This is what happens when a hill has the unfortunate destiny of getting in the path of an advancing glacier. That glacier will scrape over one half of it on its way past, and it's going to take my hill and essentially turn it into this big wedge, okay, where the glacier scraped off that side and then fell off the other side here, making this sort of wedge shape. Glacial drift, also known as glacial till, is what the material that is deposited by a glacier is called, that weathered and eroded material, the chunks, the debris. Then you can find that in several different sizes, right? So glacial till is typically anything from sand-sized to cobble-sized, any larger debris. And then rock flour is, or stratified drift or till, is what we call it when it's very, very thin, very, very tiny layers of tiny particles of rock. It literally has the consistency of flour. Flour, have you ever felt flour? It's so fine it almost feels like a liquid. That's how pulverized this rock can be by the passage of a glacier. All this material makes its way downhill through moraines, which are the deposits of sediment on the surface of a glacier that we talked about. Okay? So we get, there are several different types of moraines. There are lateral moraines, which are these ones that run along the side of my valley. This is where my glacier is scraping material off the side of my valley, like this, and that material gets stuck on the side of the glacier and makes its way downhill. The conveyor, this glacier is basically acting like a conveyor belt, okay? Scrapes all this material off the side of the glacier, or off the side of the valley, and carries it downhill. Well, when two glaciers run into each other and make one bigger glacier, the two lateral moraines combine here, and now they're in the middle of our new bigger glacier, and we call those medial moraines. So you can see this is a medial moraine right here. This medial moraine started when this glacier ran into here, and then this medial moraine started when this glacier ran into there. Okay? Two lateral moraines combine to make a medial moraine. Then, at the very end of my glacier, wherever all that material is currently being dumped as that glacier is melting, that's called a terminal moraine. Terminal moraines form perpendicular to the direction of travel of my glacier. So my glacier is moving generally that way. This is my terminal moraine that's forming at the end, the terminus of where it is currently melting. Now, glaciers most commonly form consistently during periods of glacial maximums or ice ages. How do ice ages form? Ice ages are commonly the effect, or the result, I should say, of a positive feedback loop. Okay? A positive feedback loop is one in which one part of a cycle feeds the rest of the cycle, which in turn feeds that first part. So in this case, what usually happens is Earth is a little bit too far away from the sun. Or there could be some biological input. By the way, this is what North America looked like. This is what the coast of North America looked like during the last ice age, maximum about 18,000 years ago. Okay? Look how big Florida is. Florida and Cuba are basically touching. At one point they did. Okay? There was a land bridge there. Okay? But some of the things that can cause ice ages, okay? Biological input being one thing. Why would biological input change something like the environment? Give me an example of biological input or biological effect changing the chemistry of our planet.
Well, didn't you say like about volcano, like whenever the ash goes into the atmosphere, that causes the sun to be fogged off a little bit, or for a while, and then that can like cool down the temperature of the Earth?
Yes, that is one way. Absolutely. Absolutely. Okay, so when volcanoes put ash in the atmosphere, they reduce the amount of sunlight that we receive, and we don't retain as much. Global temperatures fall. Snow line drops. More land in the snow line environment. More snow stays. More glaciers form. More ice. Why does ice have an effect here? Ice is what color?
It's like clear, like white.
It's white.
Yeah.
It's not clear. It's white, right? This is actually how we know what color our sun is. What color is our sun?
Yellow?
Everyone thinks it's yellow. It's not yellow. If you were in space, the sun wouldn't look yellow. We don't have a yellow sun. We have a white sun. How do we know that the sun is white? Because snow is white. If the sun was yellow, snow would be yellow. Right? Does that logic follow?
Wait, so why does it look?
Because it's making the light is coming through our atmosphere and getting slightly diffused and turning yellowish to our perspective. Okay? Now there are stars out there that are different colors. We just have a white sun. There are stars that are blue. There are stars that are orange. There are stars that are actually yellow. There are stars that are black. Yeah, there are stars that are brown, stars that are red. Interestingly enough, there are no stars that are green. Why are they different colors? Well, the wavelength of light that they're putting off depends on the fuel they are currently burning at that point in time. Our star is burning not only hydrogen, but also calcium, which puts off mostly white light. Okay? Stars that are burning red generally have a lot of iron being formed and torn apart in them. Stars that are blue have certain things. Stars that are black put off totally different types of radiation. Those are a whole nother ball game that I don't have time to get into. But there are no elements that are born in a star that can be used as fuel that give off green wavelengths. So there are no green stars. Isn't that interesting? Okay. I got carried off on that tangent. What was I talking about? Positive feedback loops. Okay, I was talking about the color of the sun. Why? Snow is white. Have you ever realized that white reflects heat better than any other color? Right? You ever walked barefoot on the street and you're like, ow, 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 on the blacktop, and then you get to like the white parking lot lines, and that feels way better? I grew up in Hawaii, right? So I was barefoot all the time, and I would always walk on the parking lot paint. It was way easier, way less hot. Why? Because it's more reflective. More reflective, it doesn't absorb as much heat. The more white ice we have on our planet, the more reflectivity our planet has. We call that albedo, by the way. Our planet's albedo index gets larger as more reflective ice forms on our surface. So we reflect more energy, which means that we get less heat, and the positive feedback loop continues. Snow line continues to drop, more glaciers, more albedo. Okay? That's how this works, positive feedback loop. So this can happen a couple of different ways. Like you said, volcanic input, ash, absolutely an option. That also happens from a large meteorite or asteroid impact, by the way. That's what happened with the event that killed the dinosaurs. That impact from the asteroid killed a lot of stuff that was in close proximity. The tsunami killed things even further away. But what killed everything around our planet, all the dinosaurs around our planet, was the winter that came afterward. Okay? Killed off the plants. Plants died, herbivores died. Herbivores died, carnivores died. The only things that survived, the little stuff that didn't need as much food and could live longer. Okay? Without it. Okay, so that's one way. Also, biological input. Consider this. Trees. Who doesn't love trees? Trees are great. We don't have enough of them around here, right? Trees are awesome. What do? Trees pull in carbon dioxide. Carbon dioxide, greenhouse gas. Ooh, bad. Villain. Don't like it, right? Bad. We don't want it. We put too much of it out there. Not enough trees, too much carbon dioxide. But they pull in carbon dioxide, crack it apart through the Krebs cycle, right? And then spit out what? Oxygen. They keep the carbon for themselves. That's what they build their structures with. They spit out the oxygen. Oxygen, not a greenhouse gas. Oxygen allows greenhouse gases in the first place are heavier molecules that will absorb enough energy from a passing radiation particle that radiation particle will not have enough energy to get back out into space. So the more carbon dioxide in our atmosphere, the more greenhouse gases in our atmosphere, the more solar radiation stays here and heats up our planet. If we start removing that greenhouse gas and replacing it with oxygen, more radiation can hit Earth, reflect off the surface, and go back out to space. We keep less of it. So what happens here? And when you take 1404, by the way, you're going to see this happen a lot as we talk about the development of life. Chloe's been hearing a lot about this right now in that class, okay? Is as life develops, photosynthesis and chemosynthesis break apart greenhouse gases, expel oxygen, more oxygen in the atmosphere, less heat retained, massive ice age. Ice age occurs, kills off a lot of life. The mere fact that trees evolved at all killed off a lot of things that were living at that point in time because they removed so many greenhouse gases from the atmosphere that the Earth's temperatures dropped and a massive extinction followed. Interesting to think of it from that perspective, huh? Having too many trees and too little greenhouse gases caused a massive cataclysm. It's not something they talk about in a world where humans are being blamed for global warming, is it? No, but it's an interesting alternative perspective here. We do need greenhouse gases. It's just such a thing as too much or too little, right? Okay. Milankovitch cycles are the most common cause or most consistent cause of these climate changes, though. Milankovitch cycles are how Earth moves around our planet, okay? Let me, here, I'm going to put you down, baby girl, okay? I'm just going to put you down for a second, just so I can hold our globe here. It's easier if I show it to you this way, all right? Here we have our planet. Our planet moves around the sun in 3 different ways. First of all, its orbit. The orbit of our planet around the sun is not circular. Did you know that? We don't go in a perfect circle. It's elliptical. However, on a 100,000-year cycle, it is sometimes more circular and sometimes more elliptical. Okay? It's not always perfectly the same. Do you know why it's not perfectly the same? Why does it fluctuate back and forth?
The equator, doesn't it move? It's like tilted and it's constantly like moving. Like
Oh, we're not there yet. We're not there yet. You're touching on obliquity here. Okay? We're still talking about eccentricity, our orbit around the star in the first place. Sometimes it's more circular, sometimes it's more elliptical. It goes back and forth.
Is that why like the days are never like the same? Like so like since Halloween's gonna be on a Saturday instead of a Friday. Since like every day like since we shift a little bit, it doesn't really.
It's not so much that we shift a little bit.
Yeah.
A true Earth day is really only 23 hours and 49 minutes. We call it 24 hours because we round, but that's why every 4 years it all adds up to the point where we have an extra day, okay? Just to make things work out mathematically. That's what we call a leap year, okay? But that's also not quite what I'm talking about. Earth goes around our sun how many times a year? Once. That's what a year is. But every 100,000 years, we're either going to be super far away or really close. Why? Because we fluctuate between a mostly circular orbit and a highly elliptical one. For a planet to move anywhere in our solar system, what is the force that causes that movement?
Gravity.
Gravity, the pull of something more gravitationally powerful. The star, our sun, is the most powerful gravitational force for us, yes? That's why we consistently orbit it. What's the next most powerful gravitational force in our solar system that could pull us a little further from the sun? No. Jupiter. Jupiter is the second most powerful force of gravity in our solar system. Our orbit is not perfectly spherical, or not spherical, circular, and also not perfectly elliptical. It fluctuates back and forth because at different points, Jupiter's orbit comes closer to us. So we are pulled closer or further away from the sun based on the proximity of Jupiter. Now this happens about every 100,000 years or so. So we have an elliptical orbit and a circular orbit. So at various points in time, we are going to be really far from the star and therefore receiving less radiation, or really close and therefore receiving more. That's eccentricity. The next thing is obliquity. You just pointed out something about our planet. What is it? Why is our planet not oriented like this?
Because we're constantly like tilting.
We're tilted. We're tilted. Our axial tilt is this. Our equator is defined as what? The strip, the area along our planet that is always pointed directly at the sun. Okay? And it's at that tilt, about 23.5 degrees, probably because of our collision with a protoplanet early on in the formation of our solar system, the same collision that created our moon, right? I told you a little bit about this. I dive into it way more in 1404, okay? We talk about that. But yeah, tilted at about 23.5 degrees, okay? So we have our eccentricity, our obliquity, which is the axis of the Earth, versus our plane of the orbit, okay? Here's the axis of our planet, right here, versus the plane of our orbit, which is along the equator, right? Then we have our precession. Precession is, not only is Earth doing this, not only is Earth spinning along this axis, 23.5 degrees, but it's also wobbling in space, like this. It's doing this. So if you want to see, hope none of you get motion sick, Earth is doing this in space around our sun. At a couple 100,000 miles an hour, by the way. Okay? Not complicated at all. Definitely not in any way difficult to model on a computer. Right? Come here, honey. Okay? So, all of these things add up to, at various points in time, Earth is going to be simultaneously far away from the sun and have certain parts of our planet that are not good at absorbing energy quickly pointed at the sun. Like the Pacific Ocean or Antarctica or both. If Earth is simultaneously far from the sun, while Antarctica and the Pacific Ocean are pointed at the sun, Earth is going to receive significantly less and receive less and keep less solar radiation, dropping global temperatures, reducing that snow line, starting that positive feedback loop. And that is why we have fairly consistent ice ages now. About every 12,000 no, 20,000 years, excuse me, about every 20,000 years, we reach a different maximum. So our last glacial maximum ended 11,700 years ago. Ever since then, we've been on a warming trend. How much longer do we have in this warming trend before we reach our heating maximum? Approximately 8,000 years, friends. This was something that was already happening before we came around. We've obviously contributed to the whole thing, right, with the amount of greenhouse gases we've emitted. We're speeding it up, making it worse than it would otherwise have been, but we were already on this trend 11,700 years ago. Okay? We have 8,000 more years of heating to deal with before things start cooling off again. Maybe even more than that because of how much we've exacerbated the issue. Okay? Maybe it'll be 10,000 years of heating before Earth balances itself out, unless we can make some pretty drastic changes to our society, right? Okay. That's your glaciers conversation. Any questions about that? I kept that to about a 30-minute summary, right? Good deal.
Wait, so like, you know the icebergs in the ocean?
Yes.
Like where the Titanic,
Yes.
how do those like stay up?
They stay up because of their buoyancy. You remember how I said that ice, even though it is the same thing as water, is about 9% less dense? When you put something less dense into a denser liquid, that less dense thing is going to float. Wood. What's denser, wood or water?
What?
You would think wood, and yet wood floats, doesn't it? And so water must be denser. Ice is not as dense as water, and therefore it floats on it. Yeah. What else?
Is there any specific part that you think we should review, like lecture-wise?
Yes, for this exam, you should review lectures 8, 9, 10, and 11. Sorry, you walked into that one. I'm not going to tell you, like, oh yeah, study dunes, wink, wink, right? No, anything and everything that we've talked about in this class can be on this exam. So be prepared for it, right? This exam only covers 4 lectures worth of material, which is why it's only half the size of exam 1, right? We're covering half the amount of content. She's doing good, yeah. She's kind of hanging out in a ball, chilling. I like it. Hopefully it's a positive trend. She might regress a little bit over the break since I'll be going about a week without holding her at all, but well, it's all right. We'll pick right back up. I've had 3 kids. I'm used to regressions. Camera, over here. All right, I'm going to go ahead and turn off this PowerPoint, this projector, since we're all done with that lecture. No one here has any kids, yeah? No? All right. Something you learn as a parent is every time you make progress with something, there's usually a little bit of regression afterward. You potty train your kid, they go 2 weeks without, having an accident. Yes, finally. And then all of a sudden, for just a week solid, for no reason, they'll just wet their bed. Like, oh, what's going on? And it can be really discouraging, but eventually you realize, no, developing minds just experience regressions. 2 steps forward, 1 step back. And eventually the steps forward add up more than the steps back do. And that's what makes a person. But even adults go through that, Financial mistakes, usually, I find. Alma's nodding like, yep, that's the one.
Like I just went Christmas shopping. And
Yeah.
I bought myself a Christmas gift too. I was like, I might as well buy myself.
Mm-hmm. Yep, it's real easy to justify when
Yeah,
you're spending a lot of money on someone else.
And I was like, ugh, Klarna. Like,
Mhm.
I regret going on it. But
Oh my goodness. Yes. Yes. Although I will say, the 2 steps forward, 1 step back does get there eventually too. I've reached the point where I couldn't care less about my own birthday, you know? Like, I won't buy myself a gift. And when my wife is like, what do you want for your birthday? I'm just like, whatever. Get me a book, right? I love books. But I'm like I don't like have an Amazon wish list full of things that I want, right? I've reached that point where my life is too occupied with other things than myself that I just don't care anymore. Which is both simultaneously a good and bad place to be, I guess. But it's part of growing up.
Yeah, I feel like it gets to a point where it's just like so many things to do, and I just like don't know how to do it, you know?
Yeah, and also, you reach a point of responsibility, like especially when you're a parent, you're responsible for yourself and other people, like a wife and 3 kids in my case, where the things that you need, like really truly need, are not things you can put off. And so you find the time and money to get the things that your family needs right now, right? Like my daughter needs a new winter jacket. That's not something I can wait for. It's already cold. I'm not going to wait until Christmas. So I get her that. And so by the time Christmas rolls around, I'm like, I don't know what to get. Because the things that we need are things that we need in the moment, and I get them in the moment, you know? It's more of a want thing, and I spend so much time thinking about the things that my family needs. It's a hard time for me to think about things that are wanted. I mean, my daughter will always say she wants a Barbie, right? She's easy. I just don't know what to get or think about what other people can get for myself. I take care of the needs. Ugh.
Like for me, it's gotten to a point, like for my little cousins, instead of asking them what do you want, I just give them like a gift card or like a Visa card, because I'm just like, I can buy you something and I think you'll like it, but if you don't like it, I'd rather you spend the money I'm gonna spend on you buying something you like.
So that's my default. And I wish I could say that to everyone. Just give me a gift card. That way, whenever there's something that I need later on in the year, I can use some money that they gave me to do it. My family is all about that. My family are so practical. My mom is like, hey, what do you want? I don't know. How about a gift card? Yes, perfect, thank you. Doesn't think anything of it. It's just as valuable to her as an object would be. My wife's side of the family, though, a gift card is a cop-out. A gift card it's not personal. It has no meaning. There's nothing significant about it. And so I'll say, I mean, I don't need anything. They could just give me an Amazon gift card. And my wife looks at me like, no, I'm not doing that. You need something nice. I'm just like, I can get something nice for me and myself in March, when I think of something I want with a gift card, instead of being in the moment right now and I have to make something up. I can't tell you the number of times I'd have to just make up a BS gift because they don't want to get me a gift card. It's like, yeah, I could use another backpack. I have 4. I don't need that many backpacks. But family, what are you going to do?
That's how I'm with like birthdays, because like for me, my birthday, I don't really like celebrating birthdays because I'm just like it's like just another day, right?
Right.
And so I forget that people are like, oh my god, it's my birthday, and I forgot this year that it was my cousin's birthday, and I was like, oh my god.
See, forgetting your birthday is fine. Forgetting someone else's is a whole other deal. If I forgot my wife's birthday, I'd be in so much trouble. So for years I've teased her because her birthday is October 12th. For some reason, like a few years after we got married, I told someone it was on October 13th, just for fun, because it was like that year was like Friday, October 13th. And they're like, oh, when's your birthday? I was like, it's Friday, October 13th. And she found out and she was like, you forgot my birthday. I was like, no, it was a joke. It was supposed to be this funny thing, And ever since then, I always joke with her and I put it in our calendar. We have a shared calendar. I'm like, Jessica's birthday on the 13th. And it still pisses her off. But it's so funny now. It's a little private joke. Yeah. This year on my birthday, I was performing at the Globe, so I didn't do anything, right? I did the performance. But like the rest of the day was just absolutely normal. But I guess my wife probably told them that it was my birthday because like the show ended and we did like our bows, our curtain call, and then we were all like going out to join the crowd. And then all of a sudden everyone is singing happy birthday to me. I was like, what is happening right now? Like, there's like 80 people in the audience all just kind of watching us while the whole cast is singing happy birthday. And I'm like, thanks, guys. That's really sweet, actually. But we should go talk to these people. It was really cool, though. It was very sweet. Okay. Other questions? I'm glad you've had your fill of glaciers. What about deserts, running water, groundwater, or shorelines in the ocean floor?
On lecture 2, it said something about angle of repose. Is
Yes.
there like a certain angle, or does it go from like object to object?
Angles of repose depend upon the material in question.
Uh-huh.
Okay, so not only the type of material, but also what the shape of the material is. The more angular your pieces, like Legos, for example, the steeper your angle of repose can be. The smoother your pieces, like marbles, the gentler the angle of repose can be, right? Because the angle of repose is defined as the angle at which any object can be at rest without falling under the influence of gravity, right? So if I pile up a bunch of Legos, I'll make a pretty steep pile. They're going to have enough frictional surfaces to hold on to each other. If I pile up a bunch of marbles, they're all going to roll out from underneath of each other. Eventually I'll get a pile, but it'll be nowhere near as big or as steep as the one that made from the Legos, right? That's your angle of repose. Depends upon the materials and the shape of those materials in question.
And what was the definition for mass wasting again?
Yeah, mass wasting is when something falls under the influence of gravity. So it's not being pushed by water. It's not, it hasn't been blown by the wind. Gravity is the driving force of its movement.
And that's like, for example,
Um,
that you were showing us about in the sea, right? Because like the waves were hitting like the area where the sheet was like less thicker, and so that's why it caused the arches. But sometimes
Oh, I see what you're saying. Yeah, exactly. When the top of an archway collapses, it's because it no longer has enough support to fight gravity. Gravity takes over, and the top of that arch falls in. That's called mass wasting. Yep, that's a good example there. What about you, Medusa? You have any questions? Too many. All right, I need to get some more M&Ms over the holiday and sort them out. I forgot about that.
Yeah, you can buy them still, right?
Yeah, from the M&M store. But for me to buy from anything online like that for the department, I need to have that seller as a registered merchant for the college. So I would have to register the M&M store, which is a whole process. It takes weeks. So I guess I could start that process now. I just need to remember to do it. Because they need to send their W-9 and all of their tax information to the college, and the college needs to get them approved by the state as a licensed merchant. And then I can buy whatever I need from them, but then someone else in our purchasing department actually buys it. I send in a purchase order, someone over there buys it, then the purchase order goes through, and then they send it to here, and then they have to deliver it to me, and it takes a long time. I just keep forgetting to do it because I hate going through that process. I'm much more of a do-it-myself kind of guy. I hate red tape, but I work at a college, and all they do is red tape. So,
could you go over the definition for a geothermal gradient again?
yeah, geothermal gradient is the rate at which heat increases the deeper you go underground. And that heat increasing is because the core of our planet is constantly being heated by the decay of nuclear particles, unstable isotopes, most of which are heavier, contain more mass than the other particles on our planet. And so as time goes on, as billions of years pass, they kind of slowly made their way to the center of our planet because that's where the pull of gravity is yanking them. Okay, so the lighter elements stay near the outside, the heavier ones get pulled closer to the middle, and most of those heavy ones are unstable isotopes in the process of decaying and releasing all that radioactive energy.
Geothermal gradient, it was towards the end of the 8th month.
Geothermal gradient is something we discussed when we were talking about volcanoes, but it's also come up a few times since then.
Yeah, I found it with groundwater heat. Or, yeah, because of the geothermal gradient and the geothermal energy. Which, yeah, but I think they go hand in hand. Since, like, I think geothermal energy is like power plants tap hot water, so I think the power plants use the hot water, which goes through like geothermal gradient to get that geothermal energy.
It's really funny to see what objects in the room she like latches her eyes onto. When I move like this, I see her head swaying back and forth, so I can see what object she's looking at right now.
The deeper we go, it's worth finding.
That poster
And then
is about where she's looking right now. She's got her eyes focused on it.
Got a lot of colors on it.
It does, yeah.
And you said that it emits heat because the isotopes are being broken down?
Yeah, so radioactive decay occurs because an isotope, an element, is unstable in its current state. This happens because it gains or loses neutrons. When it's unstable, it is going to shed particles off of itself. So it's going to blast electrons, neutrons, and protons off of itself until it reaches a stable condition, because all things in nature are seeking a state of stability, right? Until it does so, it's going to keep blasting those particles off of itself. And when we're talking about the sheer quantity of unstable isotopes in our planet, that's a lot of radiation being bombarded all the time. That radiation, in turn, is going to make a chain reaction, which causes other particles to become unstable and is going to make them bombard radiation. Now, this is the concept that occurs inside of a nuclear reactor. A nuclear reactor happens when you take a certain quantity of unstable isotopes and you put them in close proximity to each other. You start a chain reaction within which enough energy is released through radiation that it causes other isotopes to break down and start releasing that energy as well. You end up with, in the end, you end up with a lot of extra neutrons from all of this, because the most common way to reach a new stable state is by shedding electrons or neutrons more than anything. So you end up with a lot of neutrons. Neutron radiation is what causes the chain reaction for more things to break down. In a bomb, you don't control that. It's a runaway effect. Your bomb explodes when all of your fissile material goes through this chain reaction and releases that energy nearly simultaneously. In a nuclear reactor, you control that by putting some sort of catalyst in there that absorbs the extra neutrons. Most commonly, graphite is used in a lot of reactors. Pure graphite has the ability to absorb extra neutrons. And so what happened in, say, like the Chernobyl reactor incident, it was unable, the graphite absorber, there was an issue with it where it was unable to deploy. And so the effect became runaway, they were unable to control it, and the reactor blew.
Is that why, like, our bodies, like, for example, radiation isn't good for us, since, like, there's so many, like, neutrons that whenever we're exposed to it, our bodies don't know how to like react to it?
Well, what happens there is the energy of the radioactive particles blasts through your cells, it shreds cell walls, it destroys DNA chromosomes, and your body is unable to heal it. And so that's what makes random mutations. That's what makes random mutations. And those mutations are actually, when they occur in small quantities, that's what's the driving force behind evolution, which is something that we dive deeper into in 1404. But for now, what all you need to think about is when it becomes a runaway effect, when it happens too much, your body can't handle it. Simple example of this would be cancer. Cancer is what happens when your body's cells start to develop in a runaway effect, okay? It's kind of the opposite here. Your body is making too many cells in one place. Your body doesn't recognize it as a problem because it is your body doing it. So a brain tumor grows when your body is growing too many cells in that location in your brain, but your white blood cells don't recognize it as a problem because it's the same code. It's good code. There's just too much of it, and it presses on the sides of your brain and eventually kills you. Same thing with a tumor pretty much anywhere else. It's bad for you. Your body doesn't recognize that it's bad for you, though. So what we do with radiation is we bombard it with radiation. That's radiation therapy for cancer, okay? You bombard those cells with radiation and essentially shred them apart at the cellular level intentionally. So something that before was always such a danger to us, if there was ever an accident around radiation, all of a sudden we're using for medical purposes to destroy runaway cells.
And so what would, because like cancer is a tumor with cancer in it, right?
Cancer itself is
Yeah.
the condition where your body grows those cells out of control.
But what about like a non-cancerous tumor?
You mean like a benign tumor?
Yeah, benign tumor.
That's a very similar sort of effect.
Uh-huh.
Sometimes there's a different cause. That's often biochemical.
Uh-huh.
Like a lot of those will often occur as a byproduct of having something that your body has a bad reaction to,
Uh-huh.
right? Like consuming or injecting yourself with something. So those can be biochemically created. They can also be the result of mutations, just not in a way that is dangerous to your life, right?
So that's why like a lot of, because like my sister, she had PCOS and she had 2 tumors in her ovaries.
Okay.
But they were benign.
Okay.
And so whenever, like how they removed it, they just like did like the incision and then like they laser cut it off.
Right.
Like they didn't like fully open her.
Right, yeah, and if it's easy to do that, then of course you should do that.
Yeah.
Yeah.
And so like, but like let's say you couldn't treat those benign tumors with the radiation since that was
I suppose you could. Radiation therapy is it's one of the more intense
Uh-huh.
therapies. So there's chemotherapy and radiation therapy, both of which carry risks because they have side effects. When you receive radiation therapy, and often chemotherapy as well, one of the effects is you lose your hair. There's this big misconception that you lose your hair when you get cancer. You don't. It's the treatment that makes you lose your hair, right? So there's lots of side effects that come with risk. Being sick all the time, not being able to keep your food down. Your immune system is often wrecked as well. It's an unfortunate victim when you receive chemotherapy. So you're much more prone to things like the flu or the cold or things like that. But it's kind of a pro-con thing that you have to decide when you're fighting cancer. Save yourself from cancer and risk all these other things, or not.
Yeah, because it's like, I don't know, I feel like cancer's like really sad. You just get to limit.
It is, but it's becoming more common. And this is something else we talk about in 1404, is the genetic predisposition towards these things is something that keeps getting circulated in our society. Because normally in nature, non-positive mutations are eliminated from the gene pool. Normally, if someone is born with a genetic predisposition towards a life-threatening disease, they die from it often before they can share that gene through the gene pool. In our society, we treat those people and save those people, and even if they are terminal, even if it's something that can't be treated, that we still keep them in our society, which is wonderful and beautiful because we love people. But the side effect is those conditions persist, and they remain in the gene pool, and so they spread. And so we are seeing a rise in things like genetic cancer, genetic obesity, all these other genetic Down syndrome, all of these predispositions, simply because of the fact that we have applied human empathy, we have changed the progression of our own evolutionary path. because we have kept these conditions that in nature would have been eliminated a long time ago. It's a very interesting thing to think about. Please don't mistake me. I'm not saying we should eliminate those. That's not my intention here. I'm just pointing out the interesting scientific observation. Oh, you're going to come out and explore? Hello there.
What about twins?
What about twins?
Like, would that kind of be a genetic disposition?
Yes. So the being able to have twins or even multiple pairs of children at all is absolutely genetic, and it's passed. Not everyone contains that. Certain cultures have that more than others. It is a mutation, absolutely. Here's an interesting thing. How many children do humans usually have at a time?
3 to 5.
No, at a time.
Oh,
One. Typically, you'll have one offspring at any given time. Sometimes two, far less three or more, right? Statistically speaking. Okay? This is an adaptation that we developed in response to the size of our heads. Dogs, cats, snakes. They have litters of 5 to 6 to 12, right? Same with birds. Fish have hundreds, right? But they also don't have the same size of noggins that humans have to deal with. The most likely theory for why humans diverge, why primates in general, by the way, diverged from having multiple children born in litters at a time, most likely has to do with the size of our brains in our heads. None of you have had kids. I've never had a kid, but I sure have been there for all 3 of my children being born. Let me tell you, the head's the worst part. It's the biggest part, right, of the baby.
I thought it was like the shoulders that's like the hardest.
No, they're still real wiggly and rubbery. The head, I mean, still kind of wiggly and rubbery, but it's the first thing you got to get past, okay? Once the head, everything else kind of just goes from there without getting too, into it. The cost, the trade-off for having a larger brain was a larger head. Larger head meant more risk to the mother for giving birth, which meant that the fewer children that had to be born, the better for the mother. Okay? She's all coiled up to strike. Don't do it. I don't want you to. Yeah, greater risk for the mother. So most animals can have lots of litters of small children because they don't have to worry about the heads. But our children, they have large brains to begin with. They learn more intelligence over longer periods of time because of the size of that brain. It's a long-term investment. So we traded long-term survivability, that's what we got, in exchange for more litter sizes. We have fewer children that die during childhood because our children are more capable of reasoning their ways through dangers than, say, a dog. Dogs are driven by instinct, but they're also driven by hunger. We have the ability to resist hunger and instinct in favor of survivability. That's just one example, okay? It's an interesting evolutionary trade-off. What's the plan here, honey? Oh, you're looking at me now.
When are you going to grade the notes?
Oh, those don't actually get a full grade. They don't get any numerical grade applied to them. The value of those notes is applied to your lowest exam at the end of the course.
Oh.
Yeah. Yep.
For my class, are we getting a test this week too?
No, you've already had exam 2. Oh, wait, no. You should be getting the lab exam next week. You'll be getting the lab exam next week, and then the final exam the week after.
I'm excited.
Final day of class is December 7th or 8th, I think. Here, I can. Easy, girl. It's okay. It's okay. Odessa College academic calendar. There we go. 25, 26. Noviembre. All right, here we go. Term ends Tuesday, December 9th. So, just to tell you where we're going to be at. We had our exam review today. Your exam 2 will open today. We're getting lecture 12 on the 1st, lecture 13 on the 3rd, and then you're getting the lab exam that week as well. And then the following week is the 8th, which we're getting our final exam review, and the final exam will open. And then you will have until probably the 10th to take that final exam, because they're going to require me to have all of your final grades in probably the 11th. Okay, they usually require us to have final grades in by 2 days after the end of the course. So final day of class is the 9th. So I'll close the exam on the 10th, and this is probably going to go the same thing for your class as well. You're going to get one lecture tomorrow, which is going to be everything leading up to the time of the dinosaurs. Then you're going to get the dinosaurs and then the age of mammals next week, and the final exam review. It's going to be tight. Thanksgiving always makes things tight, though. And for some reason, they're ending the course on a Tuesday this week instead of on a Thursday. I'm not sure, or this term. I'm not sure why they're doing that, but they are, and we'll just have to deal with it. But we'll make it work. We might have, in your class, we might have one really long lecture day to make up for the lost time of the extra. But we'll make it happen. We'll make it work.
Do you know what the vacation for the staff is in December, like for winter break?
Oh, what the break is?
Yeah, like for the staff. Because I know, because I have to go to work. Well, I don't work Tuesdays, but
I will tell you that campus is closed December 22nd to January 4th.
oh, okay.
So it's absolutely for that, but I don't know if they keep you straight up to then or not.
Yeah, I'll probably have to talk to my director about it.
Because the last day for 9-month faculty, which includes me, is December 13th, because that's graduation. For staff that don't have to attend graduation, I don't know. It might be before then, might be after. That would be a good question for Alex, though. He would know. Okay. So everyone's putting their stuff away. Does that mean that we are thinking we're done with this review? We're confident? We're ready? Okay. Well, I'm going to end this recording then, and I will open the exam.